What is the electron configuration for O6, carbon, symbol C? Now, most of the time we think of electron configures based upon the structure that's been here for a few centuries called strict Aufbau. Aufbau being the German word for filling or filling order. Now, this basically goes with this order of 2, 6, 10, and 14, which is the number of electrons in an abstract shell, also known as quantum numbers. And that the first shell, it sort of works diagonally because the first shell goes 2, then 2, 6, then 2, 6, then 2, jumps to 10, then 6, to 10, 6, to 14, 10, 6. And you follow this order with the energies of these larger shells being lower, like the earlier systems. Now, so these are abstract rules, okay? Strictly numbers, all math and logic, okay? It also allows partial filling. So in the case you'll find here is that you'll find that it would go in shell 2 because shell 1 is full for carbon 2 and it's a 6, so there's 4 left over. There would be under strict Aufbau 2 here and then 2 of 6 here. Further, there is that fill order. You do the 2 first, the 14, the 10, and the 6, obviously depending on size, how many fit in. And further, for those D shells, it fills in the N order, but it has the energy of N minus 1. And similarly, the F subshell with 14 fills with N, but has the energy of N minus 2. Now, I'd like to explain this a little bit differently. You see, I think that subshells are longitudinal rings of electrons. That is, at the same inclination angle and the same distance, they will thereby have the same energy. And of course, they're in two hemispheres. So it is my interpretation of this. So there's a ring in one hemisphere and a ring in another. This is subshell 2p, and this is a presentation of the electron distribution that you'll find in a current textbook. And I consider that the center of this ring. Now, this interpretation comes from reading Nobel Prize winner Bose in 1924, his paper, The Proof of Statistical Panics. And he used two words that I found, cylinder surface, and then he said, I have to multiply by 2x to cover polarity. So I think the cylinder surface is these longitudinal rings, and the 2x is hemispheres, because balance around those things. Now, it's actually interesting what that proof does, because once you have these multiple electrons around here, they want to go to the axis of the nucleus, the nucleostatic axis, but they also sort of bounce off each other. And thereby you have this quantized, okay, number of units bouncing off of each other. And that becomes the effect that gives you this I that you find in the Schrodinger equation for an unknown axis. Of course, my work determines that that's particle 2 is the nucleus, so you actually have an orientation for that axis, and I can replace those Schrodinger things, but that's very advanced. Now, so what does that look like in 3D engineering? Well, I said you have two hemispheres. This is just the lower hemisphere. Understand there's a flip of it up here off the top of the paper. And in fact, we have those same sort of filling orders, just like here, but now it actually shows in 3D. You see, along the axis, we fill the axis first, it's two hemispheres. And so you line up, instead of it being 2, 6, 10, it's 1, 3, 5, 7. More importantly, it's 1, 3, interlaced 3. Because you're in two hemispheres, you can offset by 1/2 phase, 180 degrees, and get a little tighter build. So you can get two layers at the same count before having to jump up. So it goes 1, 3, 3, 5, 5, 7, 7. You also see how that path is interlaced, so it's not exactly a direct line. So the position of these outer shells is tighter than in here. So if you looked at an atom, if you could ever get it to stand still, um, it would have all of these electrons trying to be on the axis, and these subshells, the D's and the F's, would be, that's sort of like 2 layers in. And this one is sort of like 1 layer in. And that's how we do our calculations here of, and we still meet what they understood 100 years ago in the strict Aufbau system. So let's look at particularly how we diagram this. I have a system different than what you get um, in Lewis diagrams, which I think find unhelpful because first, they don't have hemispheres. The electrons are on the same side. And two, they don't have that 3D structure. You can't see anything that looks like this in here. So instead, I build a set of diagrams for each shell that builds these structures of 1, 3, 5. And these are the engineering rules: 2 hemispheres, only full subshells allowed, no partials. That's because of the Bose cylinder service logic from the proof of statistical mechanics. But also, that means there's this special transitional equatorial subshell of 3. And because if you have a cylinder, but the distance here, the height of that cylinder is 0, it can be only 1 set. Everything else would be 2 sets, so it's always doubled. And so that takes care of the even numbers well enough. But if you have an odd count, you have these sets of 3 that become the equator that make you only full subshells, but one set doesn't have a doubling. So the preference order is tightest fit, okay, poles to equator preference, and of course, only full subshells. And understand that those off-axis ones, while they may fill in this order, the positions are inside and thereby the energies for D and F. Now, the template specifically for my shell 2 template for an Arno-diagram has 2 options because you don't have an inner layer other than those 2 right in there tightly in subshell 1, right at the poles. You don't have an inner layer that gives it stability. So you don't get this full layering possible. It's an either or. Either you use a cube, an octet, or you get this 3 at the equator. Okay. In the case of carbon, we're at 4. So we're not using this right side of the Arno-diagram shell 2 template. Instead, we're using this left side, and we're trying to fill with only full subshells. Well, there it is. Strict Aufbau says that this would be 2s2 and then 2p2, a partial. Wikipedia says the same. The Arno-diagram, though, says you fill 1, that's full. You fill 3 here, and that's full. And thereby you can get a count of 1 in the left hemisphere, 1 in the right hemisphere, totals to 4 in using the subshell 2 template. Now, that's usually I want to have both sides full. So let me explain this a little bit differently. Carbon is a very special one because radial along the lens is balanced versus the nucleus. Its position is a tetrahedron, which is a half cube. That is every other corner on a cube. Okay, but that radial allocation means that you have 3, but they're not all the way here, and so that sine angle of those 3 times 3 of them happens to be the same as the energy to go out to this electron over here. In the polar direction, those 3 electrons, this one, this one, this one, as you can see, are going in 3 different directions, but guess what? Up, over, back, and over, and you're right back at the center. So there is no off-axis force when you have the 3 in the ring. As a result, you can get a stable one side hemisphere versus another for this shell 2 system for carbon. And that explains the tetrahedron and all of the bonding structures that we know for carbon.